Welcome to The Engineering Why. In today's explainer, we're tearing apart all that multi-encoder bloat to reveal exactly how Google DeepMind's Gemma 412B manages to run incredibly powerful multimodal AI locally. Look, if you've been following the AI space at all, you know that getting an AI to see and hear usually means bolting on massive, clunky secondary models. But DeepMind, they just totally changed the game by stripping all of that away. Today, we're going to unpack the elegant, encoder-free architecture that makes this whole thing possible. Okay, let's take a quick look at our roadmap. We'll start with the multi-encoder bottleneck, then look at going encoder-free, shrinking vision and audio, unified tuning and memory, and finally, local apps and agents.
Section 1. The multi-encoder bottleneck. Right. To really appreciate what Gemma 412B gets right, we first have to understand the friction and memory fragmentation that's been holding traditional models back from running efficiently on our consumer hardware. In a standard setup, when you hand an AI an image or an audio file, the main language model can't just process it right away. Nope, it actually has to wait. It waits for a totally separate, smaller transformer model, the encoder, to chew on that data, process it, and finally spit out embeddings that the LLM can understand. This whole multi-stage process severely fragments your system memory and adds some serious latency to your applications.
550 million. Yeah, let that massive number sink in. That represents the 550 million parameters weighing down traditional vision encoders in medium-sized models, like the previous Gemma versions. Imagine a translator who absolutely insists on reading an entire, massive encyclopedia every single time before letting you speak a single word. That is exactly what your traditional vision encoder is doing. It's over 500 million parameters just acting as a translator before the language model even starts generating a single token. It's basically a massive, bulky toll booth sitting right on your data highway.
Section 2. Going encoder-free.
So Google DeepMind looked at that toll booth and asked, well, what if we just bypass it completely? In an encoder-free architecture, you aren't waiting around for a separate vision or audio model to pre-digest the information. Instead, raw vision and audio data feed directly into the LLM backbone. By stripping away those external encoders, the large language model takes on the processing burden directly. It uses its own massive internal brain, those deep attention layers, to make sense of the visual and audio logic without any external translator. The result? It drastically reduces latency, meaning developers can now run highly capable zero-latency multimodal interactions right on standard 16GB VRAM laptops. It's a real game changer.
Section 3. Shrinking vision and audio. Now, under the hood, you obviously still need something to convert pixels into a format the LLM can accept, right? You just don't need a massive neural network to do it. Remember that 550 million parameter toll booth? In traditional medium-sized vision encoders, that data is forced to wait as it passes through up to 27 heavy transformer layers. That's 27 sequential steps of processing before the LLM can even say hello.
The solution? DeepMind dropped it to just a single layer. Yes, for Gemma 412B, they replaced those 27 layers with a new, highly efficient single-layer vision embedder. It literally takes just one single matrix multiplication to project the raw pixels directly into the LLM's hidden dimension.
The memory efficiency gains here are just absolutely staggering. We're dropping from 550 million parameters all the way down to just 35 million. But, you might be wondering, without a massive encoder doing the attention processing, how on earth does the model know where a patch of pixels belongs in an image? Well, they solved this by using factorized coordinate lookup matrices. Think of these X and Y matrices as a coordinate grid on a map. They inject spatial awareness directly into the input, so the LLM knows exactly where each pixel patch belongs. Plus, instead of pooling tiny 16 by 16 patches, it takes larger 48 by 48 pixel patches directly. The LLM simply does all the heavy lifting from there.
And honestly, the audio solution is even more elegant. Traditional Gemma models used an audio encoder with 12 conformer layers. Gemma 412P, it bypasses those 12 layers completely. Instead, you just take the raw 16 kHz audio wave, slice it into 40 millisecond frames, which, by the way, is just 640 floating point numbers, and literally shoot those raw amplitude samples directly into the LLM via a linear projection. Since audio is already a sequential time series, you don't even need those extra positional embeddings like you do for vision. It is incredibly fast and wonderfully simple.
Section 4. Unified tuning and memory.
Now, with the hardware stripped down, we get a massive advantage when it comes to fine-tuning. If you're an ML engineer, you absolutely know the historical nightmare of code tuning separate frozen encoders.
If you wanted to fine-tune a multimodal model for a specific task, you had to juggle updating the LLM weights while tiptoeing around the separate, frozen weights of the vision and audio encoders, just desperately trying to keep everything aligned without breaking the model's underlying understanding. Well, guess what? You no longer have to do that.
Because vision, audio, and text share the exact same unified weights inside the LLM, it honestly feels almost like magic. Your tuning pipeline becomes incredibly streamlined. Downstream adapters like LoRa naturally update the entire multimodal token loop in a single pass. You just apply your fine-tuning via Hugging Face or Unsloth, and boom, the model learns to process text, audio, and vision for your specific use case simultaneously. It's vastly more memory efficient and so incredibly developer-friendly.
Section 5. Local apps and agents.
Okay, let's transition from the architectural math into real-world execution. Because what can agents actually build with this low-latency capability right on your local laptop? Well, DeepMind demonstrated Gemma 412B easily ingesting a 5-minute chunk of a Google I/O keynote. It was extracting frames at 1 frame per second alongside the audio and prompt, and reasoning over the whole thing locally. Even cooler, thanks to its agentic reasoning, you can use Gemma skills to have the model autonomously code a Python Gradio app to process images. And get this, an app that is then powered by the very same model that built it. And you can run all of this locally, avoiding the cloud entirely, using tools like llama.cpp or the new Google AI Edge desktop apps for Apple Silicon.
And if you want to integrate this into your existing coding environment, serving this up to standard integrations like Continue or Aider is ridiculously simple. You just run the lightrtlm CLI command. It instantly spins up a local OpenAI-compatible API server. By matching context history perfectly in memory using stateless prefix caching, it instantly bypasses prefill latency. That means your local coding agents aren't just smart, they actually feel lightning fast.
So we've seen how stripping away heavy multi-stage encoders and projecting raw data straight into the LLM unlocks massive speed and memory efficiency on everyday hardware. The friction is completely gone. So what zero-latency multimodal AI application will you build locally today? I hope you're feeling inspired to leverage this elegant encoder-free architecture. Thank you so much for joining me for this explainer, and please remember to subscribe to The Engineering Why.